Okay, last class. Um, so the final for this class is scheduled for Monday, Monday of next week, um, at 2 o'clock. So it would be 2 to 4. It's just going to be a 2-hour test. Um, and I can be flexible if that is hard with your final schedule, especially for the people who have dynamics too. I don't think you should have to take back-to-back finals like that. So just send me an email if it works better for you to take the final a different time, and we can work with that. But if you want to take it with the class, it's 2 o'clock on Monday in this room. Yeah, and I'll put all that on D2L. Okay, so the first question was number 2 from the assignment. We have this structure that is not a truss.
Because there are external loads on it applied to it.
So the reason it's not a truss, I mean, what a truss needs is for every body to be a 2-force body. So there can only be 2 point forces on every body for it to use the rules of a truss to solve it. So this top horizontal body has a distributed load, so that doesn't qualify. And the vertical member, notice, has 3 forces and a couple on it, so that's not a 2-force body. You actually could treat that diagonal body as you could sort of do a hybrid thing where you treated that like a cable that could have positive or negative tensions. And that would work fine, and it would save you a couple of equations. But I'm just going to go through the sort of the full approach. And for the people who took statics from someone other than me, the way I'm doing this is going to look weird, but it's the same as like you could solve it using the approach for frames, I think, that you learned in your statics class. So let's go through this. I'm going to call this body 1, body 2, and body 3. And just for reference, I'll call this A, B, C, and D. And I'm going to go through each body. I'm going to do the rigid body analysis for each one. I'll get a big system of equations, then I'll just solve the big systems of equations. It's kind of a no thinking required, just knowing steps kind of approach. So free body diagram of body 1. I think we're neglecting the masses, hopefully. Looks like it. So we have down here, this is a fixed joint, so we have a force vector RA and a couple MA. And then at the midpoint, we have the force on body 1 by body 2. And then at the top, we have the force vector on body 1 by body 3. And I'm going to put my about point down here, and I'm just going to go through the whole table. This is something that we did a million times in my statics class, but if you took statics from someone else, you didn't see any of this stuff. But so I'm going to start with RA. The row vector is 0. Force vector is RAX, RAY. Cross product is 0. Then I'll go to the couple MA. We don't care about this stuff. And it just produces a moment MA. And then I'll go to F12. The row vector, this full thing is 2 meters long, and it's 1 meter to the midpoint. So From the about point to that force at 0, 1, the force is F12x, F12y. Cross product is negative F12x. And then last is the force F13. That row vector is 0, 2. Force vector is F13x, F13y. Cross product is negative 2 F13y. So, yep. Okay. And so now I can add up all the force vectors in the table, set it equal to 0 for Newton's second law. And I can add up all the couples, all the moments, and set them equal to 0. And that's the rotational version of Newton's second law, the moment equation. So I'll go, I guess I'll write all these steps out. So RAX, RAY plus F12X, F12Y plus F13X, F13Y is equal to zeros. And then the moment equation says MA minus F12X minus 2F13. This should be X, not Y. Is equal to 0. And I'll write this out in an equation form because, like I said, we're just going to end up with this big system of equations. So my first equation for my system says RAX plus F12X plus F13X is equal to 0. My second equation says RAY plus F12Y plus F13Y is equal to 0. And my equation 3 star says MA minus F12X minus 2F13X is equal to 0. Okay, that's 3 equations, a bunch more variables than equations, so we can't solve anything yet. And so now I'm going to go to body 2. Now this is the one that's a 2-force member. So you could make the assumption that this just, I guess we would have had to do it in the first body too. You could treat this one like it's just a cable, except that it can have positive or negative tensions, and that would work fine. But I'm going to just keep going with this full approach that we used to do in statics. So down here, we have the force on 2 by 1. And Newton's third law says that that's negative force on 1 by 2. And then here we have the force on 2 by 3. And that's all that's acting on this body. What do we know about this thing? I guess we know it has a height of, we know it has a height of 1 and a horizontal length of 0.5. And I'll put my about point here. So I'll start with the force negative F12. Row vector is 0. Force is negative F12x, negative F12y. Cross product is 0. And then I'll do my force F13. Row vector is 0.51. Force is F23x, F23y. Cross product is negative F23x. And so my equations say negative F12x, negative F12y, plus F23x, F23y is equal to 0. And the moment equation says negative F23x is equal to 0. Okay.
That corresponded to some wrong. That should be minus 2.5.
Yes. Thank you. Yes, I totally did that cross product wrong, and that answer doesn't make sense either. So I'm like, what's going on? Okay, so we got 0.5 F23y minus F23x. And so this equation says, I'll rearrange it, negative F23x plus 0.5 F23y is equal to 0. And so our equation 4 star says negative F12x plus F23x is equal to 0. 5 star says negative F12y plus F23y is equal to 0. And 6 star says negative F23x plus 0.5 F23y is equal to 0. So now we have a total of 6 equations, but we still, if you add up the variables, there's too many. So we have to go to the third body. And this one, we have a uniform distributed load and a length of 1.5 meters. So if I'm going to represent that as a total point force, the centroid is at the middle, and the total force is 1,500 newtons. So we have 1,500 newtons there. And then at D, we have the force on 3 by 1. And another way to write that is negative F12, negative F13, sorry. And I'm going to use that because we already have named that variable. And then this one is the force on 3 by 2, or negative F23. And I'm using that because we already have a variable F23.
You got the 5,000?
Yes, 5,000. And I guess I'll put my about point here. So I'll start with my negative F23. Row vector is 0. Force is negative F23x, negative F23y. Cross product is 0. Then my negative F13. Row vector is negative 0.50. The force is negative F13x, negative F13y. Cross product is 0.5 F13y. Then my 1,500. The row vector is negative 0.75. 0. The force is 0, negative 1500. And so that is 1125 positive. And then last is that 5,000 Newton force. The row vector is negative 1.50. The cross product is 0, negative 5,000. The force. And then the cross product is positive 7,500. And so again, if you add these all up, set it equal to 0, you get a seventh equation. 7 star says negative F23x minus F13x is equal to 0. Equation 8 star says negative F23y minus F13y is, yep.
The 1500 shouldn't be like on the x direction negative 1.
Which one?
The 1500.
The whole thing is a length of 1.5.
Yes.
So from the about point, which I put at C, that is 0.5 to get to D in the negative x direction.
Yes. And another
And then,
5 to get to the
yeah, so 1.5. Negative
No, I'm
1.5.
talking about the 1500.
Oh, the 1500. That is halfway across, so that's negative 0.75.
Oh, that's halfway.
Yeah. Okay, so we got these, and then they add up, moving the constants to the other side, positive 6,500. And then equation 9 star, the last one, says 0.5 F13y is equal to 8625 negative. And now we have this system of 9 equations for 9 variables. I like this part of these problems. It's like arts and crafts time. Like scrapbooking. Okay, so we have equations 1, 2, 3, 4, 5, 6, 7, 8, 9. And then variables, we have RA, X and RAY, F12X, F12Y, F13X, F13Y, F23X, F23Y, and MA, and then this is the constants. And so equation 1, we have coefficients of 1 for RAX, F12X, and F13X. So 1, 1, 1, and everything else is zeros. And then the next one is just the y's of the same stuff. So RAY, F12Y, F13Y. And then equation 3, MA. I don't think I can remember this. So MA is 1. F12X is -1 and F13X is -2. So F12X is -1, F13X is -2. And now we go to body 2. Equation 4 says, so it's F12X and F23X, -1 and 1. F12X is -1. F23X is +1. And then the same thing with the y components. And then F23X is -1. And F23Y is 0.5. And then the last three, F23X is -1. F13X is -1. And then you have the y components of those, and you also have a constant of 6,500. And then F13Y is 0.5, and the constant is -8625. We have to draw, we have to put all the external loads on this body. So if I draw a free body diagram of member 3, that was the horizontal member, we have this distributed load that I think was 1,000 newtons per meter. And we have the 5,000 here. And here at the joint, I think this was the one I called D. This is the force on 3/1, or negative F12, negative F13, sorry. And so I'm going to take this vector that I got for F13, and I want the opposite of that. So this is 53, 75, 17,250. And then this force is the force on 3/2, which is negative F23. So that one is negative 5375, negative 10,750. And if you plug that, now if you went and did Newton's laws on this, if we got the right answers, everything would come out to be in equilibrium, you know. It would satisfy forces equal 0 and moments equal 0. Okay, so now I'm going to do my cut 1. And this is valid for x's from 0 to 0.5, 0 to 1. And I'll first draw it with the distributed load. So we have 5,000. We have this distributed load. And we have our internal loads. And this length is x. So now if I think about that uniform distributed load, it has a width of x, a height of 1,000, a centroid right in the middle, and the area of this is 1,000x. So when I replace this distributed load by a point force, it's going to act at that centroid, and it's going to be a downward force of 1,000x. So now I'll redraw this. We have the 5,000. We have the 1,000x and the internal loads. Newton's second law says -5, nope, that's down. So 0, -5,000, plus 0, -1,000x, plus t -v is equal to zeros. And so t is equal to 0, and v is equal to -1,000x minus 5,000. And then the moment equation, we have a negative moment with a moment arm of x over 2 and a force of 1,000x plus m minus vx is equal to 0. So m is equal to 5,000x squared minus 1,000, this is x squared, minus 1,000x squared.
Would it be 500?
Yes. Minus 5,000x. And so put that together and you get a bending moment of -500x squared minus 5,000x. There's also a cut 2, but I'm just going to skip that for now. Draw a stress tensor for a point on the midpoint of the horizontal member. Okay, so in order to do that, so at the midpoint, we're talking about x equal 0.75. And we're going to calculate our stress tensor as the sum of the one due to tension, the one due to bending moment, and the one due to shear force, and the one due to torque. But the one tension is equal to 0, torque is equal to 0. So we only have these two left. And then let's see. So it says find the stress tensor for a point halfway. So at the midpoint, halfway between the center and the top of the cross section. So let me draw this cross section. It has a width of 5 and a height of 0.3. That is really fat. So, something like this. Okay. And the neutral axis is here. Our line of interest is here.
That would be about 0.075 meters from the neutral axis.
Exactly, yep. So this distance is 0.075. And I guess I'll start with bending moment. So the stress due to the bending moment is an XX stress, and it's equal to negative my over I. I is 1/12 times the base, 0.05, times the height cubed, so that is 0.00135. Y is the height above the neutral axis of the line of interest, which means if the line of interest is below the neutral axis, it should be negative. This is above, and our Y is equal to positive 0.075. And then our M, we'll get that from our internal load calculation. We just have to plug in 0.75 to this. So negative 4031.3. And so sigma XX is equal to negative of negative 4031.3 times 0.075 divided by 0.00135. And that is 2.240 times 10 to the 5 pascals. So our stress tensor so far is 2.240 times 10 to the 5, and zeros everywhere else.
I think I got 1.125 for the area moment of inertia, not 135. Yeah.
Oh, I didn't divide by 12. Dang it.
Times 10 to the negative fourth. Yeah. Too.
Okay. So this is actually 1.125 times 10 to the minus fourth. So 2.6875 times 10 to the sixth. Is that what you got?
I was gonna write in megapascals at that point.
Yeah. 2. I'll call it, well, I'll write it all. 2.6875 times 10 to the 6. And now we'll go to the shear force. This is an XY shear stress, and it's equal to negative VQ over IB. So first, let's calculate that Q. Here's our neutral axis. Here's our line of interest. The area is this. And this height is 0.075. So the area is 0.075 times 0.05. So 0.00375. And then the distance we want is this. So that's 0.075 plus half of another 0.075. Okay, so this D is 0.1125. And so Q is the two of those multiplied together. So 4.219 times 10 to the minus 4.
These from the center of the area to the neutral.
Yes, from the neutral axis to the centroid of the area, exactly. And our V, remember our X is equal to 0.75. So V is negative 5750. And so tau xy is equal to negative of negative 5750 times the Q we just got, 4.219 times 10 to the minus 4th, divided by I that we got before, 1.125 times 10 to the minus 4. Times the width of the cross section at the height that we're looking at. So since it's rectangular, that's the same at every height, 0.05. And I got 4.313 times 10 to the 5th. So the stress tensor due to the shear force is 0, 4.313 times 10 to the 5th, 0, 4.313 times 10 to the 5th, zeros for the rest. And now you can just add those two stress tensors together. And our total stress tensor is 2.6875 times 10 to the 6, 4.313 times 10 to the 5th, 0, 4.313 times 10 to the 5th, and zeros. Any questions about that? Okay. So now what are the max normal and max shear stresses? Well, what are we going to do to get those?
In order to get the principal stress,
Mhm.
we need to do eigen.
Yep, that's right. So we'll just calculate the eigenvalues of this. That'll give us our principal stress tensors, including our maximum normal. And then we can just use the formula for the maximum shear. So the principal stresses are, I got 2.755 times 10 to the 6, negative 67,520, and 0. So the first one is the max, the second one is the min, the third one is the middle. And then my maximum shear stress is the maximum principal stress minus the minimum principal stress divided by 2. (1.411 times 10 to the 6 pascals. Under what conditions would this be a useful thing to tell you whether something was going to break? What kind of material, what sort of traits of a material would make this useful in predicting whether it would break?
I think it would be like steel because that's megapascals range.
Well, I'm not talking about the value. I'm talking about so the maximum shear stress is useful for predicting failure in certain materials, but not very useful in others. And the determining factor is brittleness. Very brittle materials fail pretty reliably according to just a maximum shear stress. That's why, if you remember, I said that in compression fractures of a bone, you'll see that 45-degree angle. Remember that coming up? That's because bone is brittle and it fails in shear, and the maximum shear happens along that 45-degree line. Something like steel or most metals, this is not a very good predictor of when those are going to fail. You need something else other than that because they're just not brittle. They can deform quite a bit before they break.
Rock.
You want to hear something funny about rock? Rock is very brittle if you have a high loading rate, and very ductile, very stretchable if you have a very, very low loading rate.
So
well,
tectonic plates?
Yeah, right. And so that's why rock in the earth over time, molds as if it was like some kind of liquid, and it doesn't do it because it's liquid. It does it because that's what rock does at very slow loading rates.
So we haven't.
But if you hit rock with a sledgehammer, it shatters.
So this is just like pressure applied instantaneously, not like loading rates. So
Yeah, this is an instantaneous state of stress that we're talking about applying. And so for rock, we'd have to know more information about it. Like, in what way is that applied? Want to know something else that's very dependent on loading rate for how it fails, how it fractures? This is the weirdest thing. Go home and do this. Go to the drugstore, get some silly putty and do this. Okay, so you know what silly putty is, right? Like that pink stuff, and you can stretch it out, and it's like you stretch it out and it looks almost like gum or something, the way it stretches, and it'll stretch forever without breaking. That's at a relatively slow loading rate. The loads that we apply to it are relatively slow. So now take that same silly putty, put it on concrete. Well, that's true. If you do it fast, it'll still stretch, but it'll make a sharp cut. So you're starting to see the transition between a high loading rate and a low loading rate. But now take it out onto a hard, smooth concrete floor and hit it with a sledgehammer, and shards will go everywhere as if it was glass. And you'll have to go around the room and pick up tiny little shards of silly putty. When you pick them up, it'll be silly putty again, but it'll have fractured in a totally different. Isn't that so weird?
I would have thought it would just like stay together or something.
Right. Yeah, but it does. It behaves very differently for different loading rates. Okay. And then, was that the end of this one? Man, that's a long problem. Oh, no, it's not the end. Then we have to do the elongation of the top of the vertical member. Forget the strains. I'm skipping that. You just multiply by the compliance matrix.
So that's 200 times.
Yep. So now, what about this vertical member? So this vertical member has, all we care about are the forces along its length, because we're looking for elongation. Okay. So along its length, we have RA and F12Y. So RAY, F12Y, and F13Y. So 6,500, 10,750, and negative 17,250. It's 10,750. Okay, so I'm going to write it like this for that vertical member. Now this is the vertical member, but since we're about to do cuts,
with the elongation, don't we need like a cross-sectional area? Only problem with this was that the horizontal one has a rectangular cross-section.
We do, yeah, you're right. So 6,500 here. And then this was 10,750. And then this one was 17,750. And our cut one says that the tension is equal to negative 650. And cut two says the internal tension is equal to, so that would be negative 17,750. Right? And now we can go the elongation.
So we're not including the x components of the forces applied.
Right, because all it asked is about the elongation. It didn't ask for the deflection.
Deflection is horizontal, like in the weight. What's the difference between elongation and deflection?
The deflection is it's a movement of points perpendicular to the long axis of the beam.
Oh.
I lost my gloves.
You see any gloves over there? I didn't pick any up.
Probably not.
They would be, I think, Brock, right where you are probably. Okay. Good luck. Okay, so the elongation is, so we got negative 6,500 times the length of the bottom half of that beam, 1 meter, divided by, it said it was steel, right?
Yeah.
So Young's modulus of 200 times 10 to the 9, and then the area. I guess we don't know what that cross-sectional area is. And then plus negative 17,750 times the length of the second half of 1 divided by 200 times 10 to the 9 times area. And so there you go. That tells you the length change of this beam. And so you could punch in different values of the area and see, what the values would be. Or one thing you could do, we did a lot of this kind of stuff with spherical and cylindrical pressure vessels. I could say, okay, we want the elongation to stay less than this or whatever. What cross-sectional area is the minimum that we could use here? Okay, let's do the other one. Hopefully, the other one is important. This is really the last thing that I want you to understand to be ready for this test. Okay, so we got this cantilever beam with a distributed load, circular cross section. Oh, this has angle of twist. The angle of twist part is pretty straightforward because the internal torque is the same everywhere. So I'm going to skip that part, but I'm just going to make sure that we get the deflection part because we haven't done a lot of those problems. Okay. And you can just add the angle of twist thing to this. So the only unknown external loads are at the wall. Those aren't going to come up in cuts, so I'm just going to jump right to the cuts.
Wait, do we need to know the length of this?
Yes.
So there's not a length given out.
Just substitute for x or random value?
Yeah, let's just make up a value. It's 2 meters long. Okay, so cut 1. This is valid for the whole thing. X is equal to, X is in the range of 0 to 2. And then if we want, later we're going to need the equation for a line that represents this. So this is going to be y equals mx plus b. When x is equal to 0, what's the height of that distributed load? that's when x is equal to 2.
0,
0, right. Yep. And so for the rise over run, this is going to be a rise of 15,000, from 0 to 15,000 over a run of 2. And so this is 7,500x. Okay, so now I'm going to do my cut. And it has part of this distributed load, but it doesn't go all the way to 15,000. It only goes up to a height of 7,500x. Because this is x. And we have 5,000 here and a torque of 2,000 going the other way. And then we have our internal loads, T, V, M, and fancy T. And before I can do the calculations, I have to represent my distributed load as a point force. So we know that this distance, since this is x, this distance is 2/3 of x. And this height is 7,500 x. And so the area is x times 7,500x over 2. So that's 3,750x squared. And now I'll redraw the free body diagram, this time with the distributed load replaced by the point force. We still have the 5,000 and the 2,000. And then the internal loads. And my about point is going to be here. So Newton's second law says 5,000, 0, plus 0, negative 3,750 x squared, plus t negative v is equal to zeros. And so t is equal to negative 5,000. And v is equal to negative 3,750 x squared. And then the moment equation about the z-axis, we have negative moment arm of 2x over 3 times the force of 3,750x squared plus m minus vx is equal to 0. So m is equal to 2,500x cubed minus 3,750x cubed so m is equal to negative 1,250 x cubed. And now what's the total deflection? So what we're looking for this time, since this is facing the other way, is we want the deflection at that point x equals 0. And we have to go through the differential equation process. So here's what we know for the deflection. We know that the bending moment, the internal bending moment, is equal to EI times V. I guess I don't want this over here. I want it on the other side. So I'll write it like this. V double prime is equal to M over EI. Oh man, don't you wish you were in that class?
I think it was one of the students. It's Professor J. Anderson.
Oh.
Met him?
No, I don't think so.
It's like,
Oh, okay.
we might have brought out a brain.
Oh,
That was fun.
huh. Okay, so we'll go through this. We got that V prime is equal to 1 over EI times the quantity. So integrate this once, and you get 1250 over 4. So negative 1.4109 times 10 to the 6. That doesn't make any sense.
What is X?
1250 divided by 4. What is X?
Yeah.
X is still what it was for the cuts. It gives you give it an X value, a horizontal position, and it gives you the internal bending moment at that point. Oh, I just kept it as we have to just keep it as a function because we're going to do this differential equation. So, so this is equal to 312.5 x to the 4th, and then plus C1. And then we'll integrate it again to get V. So we have 1 over EI. And this should have been negative. And this is negative 62.5 x to the 5th plus C1x plus C2. Okay, well now we have to use the boundary conditions. The boundary conditions are always easier if you know them at x equals 0. In this problem, we don't know them at x equals 0. We know them at x equals 2. Okay, so you got to sort of go through all the algebra that means. So the boundary conditions, what do we know? This is a cantilever beam. So we know that at x equals 2, v is equal to 0, and v prime is equal to 0. So our boundary conditions are that v prime at 2 is equal to 0, and v at x equals 2 is 0. So I'll start with the v prime one. So I'll plug this in, and we got so we have 1 over EI times negative 5,000 plus C1 is equal to 0. We're going to have to calculate that E and I eventually. Might as well do it here. So EI is equal to Was this steel?
Yeah, so
Steel, and I is equal to pi over 4 times the radius to the 4th. So we got 200 times 10 to the 9 times pi over 4 times 0.01 to the 4th. And this is 1570.8. The higher that value is, the more this resists flexing, the stiffer it is. So we have that C1 is equal to oops, so C1 is equal to positive 3.183. And now we can update our function. And what we have is that v as a function of x now is equal to 1 over EI, 1570.8, times negative 62.5 x to the 5th plus 3.183x plus C2. And now we'll do the deflection restriction at x equals 2. So that divided by 1570.8. So this says 5.0928 plus C is equal to 0. This is C2. So C2 is equal to negative 5.0928. We'll update our function, and we get that V as a function of x is equal to 1 over 1570.8 times the quantity negative 62.5 x to the 5th plus 3.183 x minus 5.0928. And now we want to know the deflection at we want to know the deflection at x equals 0. And what we get is that something went wrong because this is equal to negative 5.0928, which is longer than the length of the beam. But that tells you that that left end, what this says, which is wrong, is that that left end of the beam is 5.09 meters below where it was before you applied those loads. So something I did went wrong in that differential equation, but I don't think I have a prayer of finding it in 2 minutes. Well, see if you can find it. Any questions about that? I promise you that that way of doing it is the right way to do it. Just some number went wrong somewhere.
You, when I did mine, I just did length of 1 instead of 2, so that kind of changed some of my results. But
Yeah.
They're still in like the 10th,
Yeah.
10th degree.
Yeah, I mean, I don't know much, but I know that if you have a 2 meter long beam like this, the left end can't be 5 meters below the.
My C value converges for like 0.08 for like C1.
Mhm. The final is Monday at 2 in this room. And I'll put all that on D2L. Okay, any questions? All right, good luck studying for the final. Thanks for taking my class. Take more of my classes. It pays my salary.
I got